So let's start talking about the ideal gas. Now, of course, whenever somebody mentions the ideal gas, the first thing that comes up to mind is the famous formula PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, and T is the temperature, and R is a constant. Now, one thing to remember is that this T is in kelvins. It's not in Celsius, it's not in Fahrenheit, it's in Kelvin. So you have to remember that. So I just say something. We know that, because it's a constant again, the Avogadro's number is 6.022 times 10 to the power of 23, and this is the number of molecules per mole. So we can just say that the number of um, sorry, the number of molecules in a mole, in a certain amount of moles, is going to be equal to the Avogadro's number times the number of moles. So, for example, if we have 2 moles, we're just going to multiply the Avogadro's number. And this is the number of total molecules. Okay? All right. But then, if we know that N is then equals to capital N over NA, we can plug it in our formula and we get that PV is equals to N over NA times R times T. However, one interesting thing is that R over NA is a constant, because R is a constant and NA is a constant. So two constants divided by each other is equals to another constant. And these values actually equals to 1.38 times 10 to the power of negative 23 joules per Kelvin. Okay, so we can just derive another ideal gas formula, which is PV equals to capital N K T. Right? This is useful for some different problems. So, for example, if we're talking about the, I don't know, pressure per single molecule, you could just say P over N is equals to, sorry, the pressure per molecule is equal to P over N times K T over V. This is pressure per molecule. Or if you want to find out, for example, how many, what is the volume that a single molecule has or can occupy as around the free, it's going to be equals to V, sorry, let's see, yeah, V over N is equals to K T over P. And this would be bulk volume per molecule.